Hello, everyone. Can you hear me? Should I get started? Yes. So first of all, I'd like to thank the organizers for giving me the opportunity to discuss our work, which was, it's essentially in these two papers here, it was work done in Sapienza. And this talk has nothing about topology. It's going to have some spin orbit, but I'm sort of a little bit shifted in this session. So let's hope that everyone learns something new anyway. So the title of my talk is Superconductivity Mediated by Soft Ferroelectric Modes. So the idea is a little bit like what you would expect from spin fluctuations, but now with ferroelectric fluctuations. So with that, let me get a little bit of motivation because there has been lately a lot of experimental evidence that there is some interplay between superconductivity and ferroelectricity, and this is something that is not, usually don't think about it in this way. So this would be the phase diagram of prototype incipient ferroelectric, which is strontium titanate. This is going to be very much motivated by strontium titanate. So you have this superconducting phase close to a ferroelectric phase. And this ferroelectric phase often can be described by this softening of what I'm going to call the soft ferroelectric mode, which is a transverse optical mode, and it's shown here for this perovskite structure. So in the paraelectric phase, it's completely, the paraelectric structure is kept, and then as you get closer and closer to the ferroelectric phase, these atoms, if you want through the transition, freeze, and the system develops a polar axis. So you get this, local dipole, if you want, with the titanium moving against the oxygen cage. That's the easiest way to think about it. Now, experimental fact, as you get the system closer to this ferroelectric phase once you dope it, because in the ferroelectric phase, if there is no carriers, the system is a ferroelectric. If you dope it, it becomes a polar metal, and now it can also develop superconductivity. So the experimental fact is that this superconducting phase gets enhanced, TC gets enhanced as you get closer, and now the question is why, and can we learn anything from the pairing mechanism? And something that I would also like to point out in these systems is that these carrier densities are extremely low, so that leads to having very, very low Fermi energies. And that puts us outside of the conventional BCS paradigm that usually we like to think of when we think of something like electron-phonon mechanism. So that doesn't work. And then what I like to discuss today is, the most natural way of thinking about this problem, which is coupling these electrons linearly to this soft ferroelectric mode. This soft ferroelectric mode is, as I said, is a transverse. So the conventional electron-phonon coupling does not work because you can think that, as the phonon propagates, it's transverse, and then Q is perpendicular to U. So, the product is zero. But instead, I'll show you how you can get still to linear order a Rashba-like coupling. And whenever I use this word, I'm thinking about it in a dynamical way because I'm always going to be outside the polar phase. So this is going to be fluctuations of this mode coupling in a Rashba-like way. And I'll also like to point out that this is not only relevant for bulk materials, but there is lately also a lot of activity going on these KTO heterostructures, this is also an incipient ferroelectric. They grow it in different directions, and it has a much higher TC, and this TC depends strongly on how you grow the substrate. So let me go into the problem. I have to say a little bit about the electronic bands. So these are, this is the FT also, bulk TFT, and actually this is also an ab initio, a tight binding model. And I'm going to be using a lot this time-binding model because this minimal model gets a lot of the physics right. And then, so these are T2G orbitals, 3D of titanium with spin orbit coupling. So I have to think about it as a J. And if there was no spin orbit, all these states would be degenerate with 3 times 2 of spin. But spin orbit opens a gap. And then this is cubic in the cubic structure. And now when you further go down into the tetragonal phase, there is a further split from the tetragonal crystal field. And now I just want you to think about these bands not as T2G, but as T2G plus spin orbit, because as I dope the material, let's say as I fill these bands, I get with a Fermi energy that is definitely comparable to this spin orbit energy scale. So I would say that that's reason to think about this basis, the spin orbit basis, as the more appropriate one. So for example, if I look at this lowest band, this would be the 3½ plus 3½ where I mix the, I'm going to be calling this X is just the X component of the 3D, so Y, Z, and so on. So, you know, the pseudo spin up would be X plus I, Y, and the pseudo spin down would be Y minus I down. So, Y down. So this is the band structure, or you know, the non-interacting electronic part, which is T2G plus spin orbit. Now, as I said, this ferroelectric mode is transverse optical phonon. It breaks inversion, so it has odd parity if you want. In the tetragonal phase, it belongs to these 2 reps, and I've mostly be focusing on this one here, which is in plane. And now, because U and Q are perpendicular, you know, I can't have the classical constant coupling. I need to go to next order in linear order to U, and that is, you sit down, you do the symmetry analysis, and you can convince yourself that essentially to linear order, these electrons can couple via this coupling, which is linear in K, and cross sigma, where sigma is the pseudospin of the electron. So how is it that I'm coupling a non-magnetic polar displacement, which is U, to the pseudospin of the electrons? And the answer is I need spin orbit coupling. So let me quickly, in a microscopic sort of intuitive way, show how this, if you want, symmetry allowed or phenomenological coupling comes into play. So this would be again, I'm showing the T2G orbitals, and now I'm going to induce a finite polar displacement, which is characterized here by these p orbitals of the oxygens displacing. And now, without this U, so if this U was 0, this hopping would not be allowed. It would be forbidden by symmetry. In place of this, in the presence of this polar displacement, there is this new hopping channel, which is allowed. And because of the symmetry of the orbitals involved, these T2G orbitals, this thing is odd. So the hopping to the right and to the left has the opposite sign. So it breaks inversion. So the first step is this interorbital hopping breaks inversion, spatial inversion. Now, if I go to the spin orbit coupling band, because this is the T2G band, now I say, okay, let me go to this pseudo-spin up and down band. This hopping is still there, but now the pseudo-spin up experiences it exactly opposite to the pseudo-spin down. So that means that the breaking of inversion is experienced in opposite ways. So like left movers and right movers are going to have a different energy, and therefore dynamically you get this kind of shift of your band, which is what people usually think of in terms of Rashba. So it's a Rashba-like band splitting, but it's dynamic. In our case, we have a tetragonal point group. That means that this K cross sigma is a little bit more complicated. And when you go to the band basis, you are allowed to have different couplings for the different point groups. But this is allowed by symmetry. What I'm going to do next is like, okay, this is allowed. It's very good. I can also see that it, it could happen through these processes. Now, how large is this coupling? And that's what I'm going to do now. I'm going to use ab initio frozen phonon to sort of estimate the coupling so I'll show it for STO. But we basically build a formalism where you can estimate it for any material in a quite straightforward, cheap way. So as I said, you put this polar displacement, you're expecting to have this shift of pseudospin up and pseudospin down in this way. That means that, for example, if I go to this band split, I look at the linear component, as you'd expect, first of all, to be linear in K, so this is the Rashba-like, and then the slope is essentially going to be proportional, or I'm going to extract from the slope this coupling strength. So that's what I do. I put, well, not me, I worked with some ab initio people who did frozen phonon calculations in the bulk at Q equals 0, and then you see how these electronic band structures are modified, and I just take the split, I plot it in the same way, I extract the linear component, and sure enough, I do see that this split for all the 3 bands of strontium titanate are linearly split. So I extract, for example, in this case, from these 2 slopes, I get tau of A and tau of B. And then once I have those, this split maybe it's not very useful sometimes. So what we had to do was to go from the classical displacement to the second quantization, go into boson language or to phonon creation and annihilation operators, and then you can derive the electron-phonon coupling, which has a characteristic bare coupling in the vertex, which is now depending on momentum, which is, in that linear momentum, which is unconventional, but then it has also a strength which is proportional to this tau. And just to give you some numbers, what we find from this ab initio is that the coupling, this Rashba-like coupling, which naively in the community was believed to be very small, it's actually quite strong and significant. And we also find that these different labels here are just the eigenvector that is extracted from different experiments. So it's not exactly clear how exactly these atomic displacements happen inside the mode. But in all the cases, we tried like 3 or 4 cases. It depends a lot on this, but it's certainly a significant coupling. So now that I have a significant coupling, the fun part comes, which is like, okay, what about pairing? I'm going to couple the electrons in this way. It's certainly an unconventional way. And what kind of superconducting state should I expect? So as a side from SEO, just from a purely theoretical playground model, I can solve the pairing problem by projecting this effective electron-electron interaction into the Cooper channel, and I can look at the different channels, pairing channels. Usually from electron-phonon, you would stop at S wave or A1G, the conventional trivial state. Something cute or unconventional about this mechanism is that even if you look at S wave, so you go to S wave, sure, it's attractive, is the leading instability, but P wave and D wave, so odd parity channels and higher order non-trivial Ls of the even parity channels are also attractive. And this is because of the momentum structure of these fluctuations. It has odd parity, and that's why it gives me this. And then it's also highly momentum dependent, and that's why I get an attraction here. Okay, so it's different from spin fluctuations, where you would have to go to different Qs and so on. This one gets it straight away. Now, going back to, I have a substantial coupling in STO. That one is an S wave as far as we know, so I'm going to focus on what I would get in STO. So I got my G. And then naively, the strength of the coupling is density of states G squared, where G is the coupling that I just estimated on this. And then you have the frequency of the mode you're looking at. And then, just before putting any numbers, density of states parabolic band goes with KF. G squared, I just told you that G is linear in K, so this is K to the cube. This looks like I would get room temperature like this. And the answer is no, there is something else. And it's that if I look at G a little bit more carefully as a function of momentum, because now I'm going to imagine that I'm filling up my bands, then sure, at low energies, low momentum, this coupling G, so whenever this is a frozen phonon DFT, so this is giving me the split, but this split is proportional to G. to G. So this is linear in K, but it does not grow up, to the infinity linearly. So it's not conventional Rashba-like. But what ab initio finds is that eventually this thing peaks, and then it decays in a form very close to 1 over K. So then we're like, oh, wait a moment, because if this is like this automatically gives me a dome in G, which will give me a dome in lambda, and then a dome in TC. So we wanted to understand a little bit better this. So in order to do that, we use this minimal model that I just described with the T to G electrons. And a lot of expectation. Yes, there you go. And it works. It works extremely well. So this is a minimal T2G model. I just put the non-interacting electronic model I discussed before, and this one parameter with this induced hopping channel. And many of the details are not covered, but the one that I'm interested, which is Rashba peak and 1 over K, or linear and K peak 1 over K, is definitely there. And then I have a minimal model, and then I can understand the physics, because now I can do perturbation, and I can play around with this model. And what we find is that what sets this behavior is a competition between two energies, the spin orbit energy, which is strongest here, and some hopping term, which switches on at finite momentum. So you do perturbation, and sure enough, you do recover that when the spin orbit dominates, you have this usual K linear pseudo like Rashba, conventional Rashba behavior. But when the kinetic energy takes over the spin orbit, then you get this 1 over K, and this spin orbit assisted coupling is no longer can no longer keep up, essentially, with kinetic energy. In a slightly different way of saying the same thing would be that you have momentum-dependent quenching of angular momentum, because when the spin orbit is the one who sets the states, then your states would be, x plus I, y, which have this angular momentum, and then as K gets larger and the kinetic energy says, no, wait a minute, I want a different eigenstate, then, this interaction slowly dies out as 1 over K. And that automatically gives me a scale for this problem to sort of have an idea of where this peak would happen. And in this case, it's given by these two parameters, which for STO, I could fit from ab initio, and then it's, around this number. That means that when I take this G, which goes as Rashba and then 1 over K into this expression, assuming a simple parabolic band, automatically, unsurprisingly, I do get a peak in lambda, okay, which is shown here. Just look at the full lines. Then that means that when I take the BCS expression for TC, and now I can convert Fermi momentum to density, usual textbook, and then I get a peak in TC as well. So this would be the blue curve from this very simple, estimation of what kind of superconducting state you would get that I got from a tandem between this minimal model and ab initio frozen phonon. And the red dots are here, shown here are experimental bulk probe TC. So I would say that the mass in density is pretty good. The magnitude that I would need for lambda is pretty good, and one even gets this kind of asymmetry in T with in carrier density. So I would say this kind of Rashba-like coupling is a leading pairing mechanism in STO. And then the last slide, I'd like to just quickly, I have 2 minutes. So I'd like just to quickly say that sort of discuss some more recent work that I've been doing also now with Giulia Venditti, who is shown here. This was on Sunday while she was preparing her talk. So if you have more questions about this, you can also go find her. She's around. So as I said, there is another system where this mechanism may be very relevant, and this is these KTO heterostructures. So now we did essentially we went through the same formalism that we had developed for STO. And now I guess the important thing for KTO is because tantalum is a heavier atom, then the spin orbit is about 14 times bigger. So sure enough, the spin orbit is 400 instead of 28. And then you plot this frozen phonon, you see what the coupling is. And the coupling is also much bigger. It's shown here, like the scales are much bigger. Again, it has Rashba-like coupling. There is also some deviation. And now, what is very interesting about this material is it's cubic. And that means that the J3 is degenerate. So this band here is rather isotropic, so what you would expect from a conventional Rashba is just a circle. But these two, you can see that the slopes are very different in different momentum directions. If I plot it in a different way in a polar plot, you see that this Rashba coupling is extremely anisotropic for this manifold here. And using the same kind of minimal model, we have also understood now why and where this K-linear, very angular, strong anisotropy comes from. And then I just wanted to mention that when you compare the numbers with STO and KTO, not surprisingly, since this spin orbit assisted interaction, this is a spin orbit assisted interaction, and the spin orbit is much larger in this material, it is very strong. So I would say this is a very promising route to look for pairing both in heterostructures and even bulk, which as far as I know, it has not been found. And with this, I just leave the conclusions. So we developed a formalism to study this generalized Rashba, which is a way to couple conduction electron to soft ferroelectric modes. You need spin orbit for this. And then I gave some estimates for STO, playing or working using both this minimal model and DFT, and we found a strong Rashba coupling, and we also found that it naturally has a dome. Without putting any other, parameters or mechanisms into it. And then, from a weak coupling analysis, that means that there is a dome in TC and there is a lambda, which is, pretty robust which make this mechanism, I would say, one of the leading candidates for bulk superconductivity in STL. And then, as an outlook, I just pointed out, KTO-based heterostructures, bulk, etc. And I didn't mention it, but I think there is, all I discussed was to linear order in U, because that's what you usually look at. This is unconventional enough that the linear order is different. And if anyone is interested, the quadratic coupling is also extremely large. We are now starting to understand this term right here, which would be basically this kind of vertex, which usually people never look at. And then it would be very interesting to see what the resulting pairing diagram would give you. And with that, I'll thank you for your attention, and I'll take your questions.
Thank you very much for this nice and clear talk. So I think we have time for one question.
Sorry, I cannot see how to indicate the question. I just can. May I ask?
Where are you? Oh, I see.
Yeah, Sergei Klimin from Antwerp. Sorry?
Go ahead.
Sergei Klimin from Antwerp. Could we look a bit for the slide with the comparison with experiment for strontium titanate for your model?
Yes, the one with TC, right, versus N?
Yes. Maybe I missed something. Do you have any fitting parameter for this good agreement?
No, so that's my point. Like I just had one parameter. So I first feed the non-interacting electrons to the FT. That's spin orbit and hopping integrals, which are 4. And then I just have one parameter, which is this induced hopping channel that is there one because of the coupling to this phonon. And the only way that enters is through this T prime, if you want, dt du, and that dt du I literally extract from DFT. So I place such a phonon, frozen phonon, I see the slope, and then that gives me some MeVs per angstrom, whatever that number is. I put the number in, and then, you know, that's it.
Okay. Okay,
and then that
thank
gives
you.
me a lambda, of course, that gives me a lambda, right? Lambda BCS. And then I'm plotting the corresponding, how the TC versus TC max would look like as a function of n. And it's extremely simple because I'm assuming a parabolic band, so it would be, basically I'm saying that the lowest band has the highest contribution, and I'm neglecting any multi-band physics and so on. So I was also quite, you know, surprised.
Okay, thank you. Because it looks a bit confusing because, as you know, there are several mechanisms, and for example, Fröhlich interaction cannot be neglected, and it always exists in strontium titanate. And this soft mode is a kind of transverse optical mode.
Yes.
In fact.
And
exactly. It is necessarily accompanied by the corresponding LO mode. It always must be present, and together with other mode, and contribute to the electric function.
Yes.
And if we combine both those mechanisms, I think other mechanisms must contribute too.
So what I would say is I'm going to answer with actually experimental evidence, which I think is...
Okay. Okay, thank you.
So with experiments, what experiments show is that taking this superconducting phase closer or larger, and you can do that in different ways, TC is very much affected. Now, you look at how the longitudinal mode or the Fröhlich interaction you're referring to is changed by these very small pressures and you know, different ways, and that doesn't move. It doesn't do anything. It doesn't care. It's very, very low energy scales. So if the leading mechanism was that interaction, why is TC, you know, having such a big effect? That was why I think it's, I started from, let me directly couple to this mode, because it's this mode that when I'm doing these small changes is changing a lot, and that's where I'm seeing how TC is changing a lot, and by a lot I mean like 50% up TC and stuff like that.
Okay,
so that's a bit the reasoning. But
thank you. I think, sorry to interrupt, but I think we have to go on. Sorry, maybe you can ask your questions during the coffee break, and let's thank her and also all the other speakers of this session again. Thank you.
Thank you.